Today we're going to cover section 8.1, arc length. So we wish to determine the length of the curve from point P1 to P2. So we're not looking for the area under the curve, but we're looking to see how long a curve is. So if we draw this in here, let me change this. I'm going to change the color because it's already in black. So, and I want to know from this point to this point here. So I'm going to call this one x sub 1, y sub 1. And I'm going to call this point over here x sub 2, y sub 2. And the length from here to here, the hypotenuse, I'm just going to call delta s. That's eventually going to be, as we get those 2 points closer and closer to each other, how we learn to do in Calc 1 some stuff. It's going to be the length of that curve. But the distance from point here to here is delta y, and the distance from here to here is my delta x. The reason I even did any of this stuff, I don't care about what x sub 1, y sub 1 is, x sub 2, y sub 2 is. It's the deltas I really care about, the change in. I can use Pythagoreans, and I can say delta s squared has to equal delta x squared plus delta y squared. And if that's the case, then delta s is equal to the square root of delta x squared plus delta y squared. Now, I didn't say plus or minus because it's a length, so length's not going to be negative. So now that I've established this part, what's interesting is I can multiply a side by a form of 1. So I have a delta x squared plus delta y squared. And what happens if I decided to multiply by a delta x squared over delta x squared and take the whole square root of that entire thing? Well, then I can multiply through. Delta s is equal to square root. Actually, I'm going to write this without the square root symbol, then put it in. I have a delta x squared over a delta x squared plus a delta y squared over a delta x squared. Take the square root of that. And I'm still multiplying by delta x squared because this here is that delta x, and this delta x squared is that. So we can see where everything's coming from. Now I can look at delta s is equal to, well, delta x squared over delta x squared. When the same thing's over each other, it's 1 plus delta y squared over delta x squared. And what's interesting is that the square root of delta x squared just is delta x. And then I could also say that delta s is equal to 1 plus, well, that's just dy dx quantity squared. Instead of delta x, I could say delta dx. I could sum all these up, and then I could get the integration of 1 plus dy dx quantity squared, take the square root of that, dx. So delta s, if I did, right, I can get my arc length. So if I want to know the arc length, I'm just going to, I'm going to call this L, my arc length. I don't need this. My arc length. If I want to know my arc length, I just take the integration of that. So let's look. It says the arc length formula says if f prime is continuous on a closed interval a through b, then the length of the curve y equals f of x from a, where x is between a and b, is L equals the integration of a to b plus 1, the integration of a to b, the square root of 1 plus the derivative of x squared dx. And then it says if g is continuous, g prime is continuous on c of d, then the interval c of d, then the length of the curve, which x equals g of y, where y is between c and d, is then the same thing. Instead of f prime of x squared, it's g prime of x squared. So in other words, I can look at the arc length, whether I'm looking at it in terms of x's or y's. And here's the formula. This formula you will need to know for your test. Again, this will be test 4, which will include sections 8.1, 8.2, chapters 10.1 through 10.6. So let's look at this. We're going to use arc length, so we know I need an a to b. I need the integration of 1 plus an f prime of x that's going to get squared dx. And instead of writing df prime, why don't we write it as dy dx squared. That's how I typically write it. So we know what y is. We know y is equal to x cubed. I know it's written here, but it's a habit of mine to rewrite it. Y prime has to equal, then, take the derivative of x cubed. I get a 1/2 x squared minus 1/2 x to the minus 2. Because this here is just 1/6 x cubed plus 1/2 times x to the minus 1. That's how I get that part. Now, I have y prime, but I need y prime squared, so I need to square everything. So y prime squared is equal to 1/4 x to the 4th minus 1/2 plus 1/4 x to the minus 4. This is something that you should know how to do, so I'm not going to go over how to FOIL it. All I did was FOIL. Now I'm integrating from 1/2 to 1. So my arc length is 1/2 to 1. Well, 1 plus this. Dx. I can combine my terms by dropping the parentheses. So I got a 1/2 to the 1. 1 minus 1/2 is a half. So I have a 1/4 x to the 4th plus a half. I'm just keeping it in this order. You're going to look at this and go, oh my goodness, what am I going to do? This looks like junk. I can't work with this. But even if you don't recognize it, hopefully you'll start seeing the patterns on here a lot of times, at least in your homework. The author went through a lot of pains to find problems that would work out nicely. And this is definitely one of the problems that would work out very nicely. This is actually the sum of squares. I mean, sorry, not sum of squares. It's a perfect square trinomial. So I have 1/2 x squared. So this factors plus 1/2 x to the minus 2 20 squared dx. What's nice is that I'm taking the square root of something being squared. So I end up with this. From there, I say, well, that's an easy integration, right? I want to integrate that, so I get 1/6 x cubed minus 1/2 x to the minus 1 from 1/2 to 1. You'll evaluate by substituting in, and you'll get your final answer. I'm just going to save some time. 31/48. Right, because by now we should be comfortable doing our evaluations of the integrations. So now we want to use the arc length formula to find the length of the curve. Y equals 2 minus 3x from where x is between -2 and 1. And we want to check our answer by noting that the curve is a line segment and calculating its length by the distance formula. So we're not going to do that part. We're just going to do the first part, finding its length. So again, y is equal to 2 minus 3x dy, or y prime, is equal to minus 3. So y prime squared is, well, just 9. So I'm going to have -2 to 1, 1 plus 9 dx, or -2 to 1 of the square root of 10 dx. Again, a very simple integration, square root of 10 times x from -2 to 1. and it turns out to be 3 square root of 10. All right, so hold on for a second. Hi, welcome back. I just decided to real quickly show you that using the distance formula like it says in here, it's just a line, right? Y equals 2 minus 3x. So I say, what happens when x equals -2? I get a y of 8. So I have the point -2, 8. And then I want, what happens when x equals 1? I put that in, I get 1, -1. So those are the 2 points. I want to find the distance from here to here. And we learned in the distance formula, it's x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. Take the square root. So I end up -2 minus 3 squared. Yeah, I wrote a positive 3 here because when I square it's going to be positive anyway. 8 minus -1 is 9. 9 squared. So I have 9 plus 81, or square root of 90, and square root of 90 is just 3 square root of 10, which is the answer we had. So we can see it works. Obviously, the arc length of a line is going to be the length of the line. So here we go. Let's get back to calculus now. So I want to calculate this problem. I know that y is equal to above, so y prime is equal to x minus 1/4 x to the minus 1, right? Because the natural log of x, when I take the derivative of f of x is equals this, f prime of x is equal to 1 over x, right? So y prime squared is equal to x squared minus a half plus x to the minus 2. I'm integrating from 2 to 4. So here's my integration, 2 to 4. I have 1 plus x squared minus a half plus x to the minus 2. Take the square root of that entire thing. Combine my terms. Right, I have a -1 and a half. I have a 1 and a negative half. So I have x squared plus a half plus x to the minus 2 dx. Hopefully from the last one we can see that this again is a perfect square trinomial. And you should hope that these are going to factor. If I'm asking you to do this on the test, they should factor something that you can work with. Right. So this is x plus 1/4 x to the minus 1 quantity squared dx. Since the whole thing is being squared and take the square root, I could just drop the square root symbol. X plus 1/4 x to the minus 1 dx. I can evaluate this, I can integrate. All right. This is x to the minus 1, so that means I'm taking the natural log of the absolute value of x from 2 to 4. So I'm going to just give you some values here. 8 plus 1/4 ln of the absolute value of 4. I can put parentheses because 4 is positive. Minus 2 plus 1/4 the natural log of 2. And my final answer is 6 plus 1/4 the natural log of 2. Because I have where that comes from, just a quick note for those of us who can't remember real quick. I'm going to take 2 seconds to show you. That's the only part I'm going to look at. I'm going to put it in red so we don't get confused. So I have 1/4 natural log of 4 minus 1/4 natural log of 2. Since they are the same, they both have a quarter on the outside, I can combine them. 4 over 2, which is 1/4 the natural log of 2. That's where that came from. So now we're going to look at this problem. All right, so y prime. So y prime was the natural log of cosine x, which means I have to take 1 over the x, or 1 over the u, so it's 1 over cosine of x. And don't forget, it says you also have to take the derivative of x, which is minus sine of x, which means I have a minus sine of x over cosine of x. That's y prime. Y prime squared means I end up squaring it, so it's going to be positive. Sine squared x over cosine squared x. Hopefully I can recognize that as being tangent squared x. So now we want to find the arc length from 0 to pi over 3. it's 1 plus my y prime squared, which is just tangent squared x dx. Hopefully I'm recognizing that 1 plus tangent squared x is just secant squared of x. We should remember that from all those problems we did in chapter 7. Since I'm taking the square root of that, it's squared. I could just write it as secant x dx. Now, I may not remember, but from my formula sheet that I'm going to provide on the test, you have this as a given. If I gave you the integration of secant x, you know that it's the same thing as the natural log of secant x plus tan x. And I'm going to evaluate from 0 to pi over 3. So now I'm going to end up with a natural log, and if I don't know what's going on, I'm going to draw myself a triangle. Here's my theta. Oop, not theta. Sorry. That's right, pi over 3. Pi over 3, pi over 6. This is 2, square root of 3, 1. But just remember, pi over 3 is across from square root of 3. I'll evaluate that. The secant of pi over 3 is 2, plus the secant, plus the tangent of pi over 3, which turns out to be square root of 3, minus the natural log. The secant of pi over secant of 0 is 1. Tangent of 0 is 0. I'm looking at natural log of 1, which the whole thing is 0. So my final answer is just the natural log of 2 plus the square root of 3. And I could drop this and just put parentheses instead of square root, instead of the absolute value, and that's fine.